meeting Professor Police in one Belgium. And today I'll talk about the mimicking of biological behavior through CMOS and beyond CMOS devices. So how many of you know about CMOS or semiconductor devices or even MOSFET? So MOSFET, anybody or all of you are on that? You all are from UC, which year? I can see all young faces. All UC, right? All UC. And final students. So they must have analog circuits and solid state devices and digital electronics, right? So I am guessing that you guys know about MOSFET. So we'll talk about all these devices and how we can mimic our human brain. And so if you see, I have a lab which is nanoelectronics in emerging devices. And we work on these areas like machine learning in devices and biosensors and biofeds and beyond CMOS. So beyond CMOS means it is without silicon. So when we talk about silicon substrate, because I also have some kind of substrates to show you. So I'll show a later point of time. But if it is not silicon, then you can call it as a beyond CMOS. And then coming to 2D devices. So 2D devices means it is two-dimensional, not like three-dimensional. So you know silicon, germanium, whatever the semiconductor, or group 4 elements, right? In the periodic table, if you see the group 4 elements normally called as semiconductors, and they are of 3 dimensions. X, Y, Z, right? So X, Y, Z means so whenever the carrier transport happens, they will go like this, again go like this from source to drain, right? And there is a high chance of scattering because while traveling from here to there, right? If I find any chairs in between, then I may find obstacle, right? So similarly, instead of 3 dimensions, if it is a 2D, so there is no Z, and it is like a ballistic transport. Or when I fire a bullet, so it will go straight, right? It will be directly. If I target your, not your, something wall or some switches, right? So it has to be there. It should not deviate from the target. So this is how 2D semiconductor devices are coming to picture. So it has no 3 dimensions. And it will support the ballistic transport or like a bullet. And the same thing, we have negative capacitance FETs, NC FET. So that I will talk why it is necessary, because you might be knowing the transfer characteristic of MOSFETs, right? I hope everybody know. But what does it mean? Transfer means output current to input voltage, right? And output means output current to output voltage. So when you see transfer characteristic of any MOS, so there you can see what is the threshold voltage and how much time it is taking to on, and what is the off-state leakage, right? So off-state leakage means at 0 voltage what is current, right? So if you plot in log ID and VG, you can easily see what is current at 0 voltage. So and there is a Boltzmann limit which is called as subthreshold slope, and there is a Boltzmann limit, it cannot go beyond 60 millivolt per decade. So why I am taking decade? Because log ID and VG. So that's what decade is coming. So it cannot go beyond 60 millivolt per decade. So that is why there is a always leakage current at VGG. You cannot avoid. So that is called leakage current, and how these NC FETs can get rid of leakage current, or you can say the threshold slope. How can we overcome the Boltzmann limit or Boltzmann tyranny? So there is some devices. And the neuromorphic computing, so like neuromorphic applications. So neuromorphic means it is mimicking our brain. Okay. So how efficiently we can mimic our brain? Suppose you compare with supercomputers, or you compare with any other HPC, high performance computing or anything, right? So no one can match our brain. Because see, I am talking now and you are listening. Maybe some of you will remember me in a bad way or in a good way, that is different, okay? But I hope maybe some of you remember. And while I am talking, you may process the information whatever I am talking, right? As well as you will memorize the things, correct? So two things happening parallelly, you can say I am processing the information as well as I memorize the things. So these are the two things which cannot happen in the current, whatever we are using the computers, right? Because we have a CPU separate and we have memory. There is a separate transit function for journey, and they may stretch and align together. So that is how your movement or mobility may increase. So this is one technology. And why I am talking all this? Because you see the innovation started in 92, but while reaching to the market, it takes time, right? It is not that today you invented and tomorrow it has been marketed, right? So it will take long time. Minimum time is 7 years, 8 years, 10 years, who knows, right? So that's what it usually on an average it takes 11 years from laboratory to market, right? So all these examples I can give you: high-K, methyl-gate exchange, it started in 96, then it marketed for mass production happened in 2007, and similarly the other technology raised source chain, multi-gate, right? Today whatever you are using, that is based on the FinFET. So FinFET means there is a three-dimension, have you heard about FinFET? Anybody? FinFET? You usually fish, right? So fish is a fin. You know which one is fin? No? Fish. Yeah, fish. No? Okay, fine. So FinFET is a, you can Google search. So FinFET is a kind of device. Suppose this is my device, right? So this is the gate. So this one is source, drain, and gate is having three sides. Okay. So instead of controlling from only top view, we can control from three sides. So that is the concept. So you have a source, you have a drain, and the channel has been surrounded by three sides. So if you apply a gate voltage, it can control from three sides. So this is the concept of FinFET, and it came around 87 or 88. But till now it is going on. Till now, the same thing, whatever processes you are using in your mobile phone or in your computers or in your laptops, so everything is based on FinFET. Till now, right? So, if I talk about 3 nanometer, 5 nanometer technologies, till now FinFET is dominating. So, the meaning is, on an average, if you start with invention to marketing, so it takes 10 to 11 years. Okay, and now like almost everybody now also we are talking about with HOD, all are inclined towards computer science. It seems like all engineering is based on computer science, right? So it is not like that, because the buzzwords came, no, AI, ML, data science, big data, or whatever, right? IoT, IIoT, industrial IoT, right? So lot of buzzwords are coming, and that is why a lot of engineering people thinking so only engineering means computer science. So that doesn't that is not at all true, because computer science can apply to any field, right? And if you see research is not basically any specific domain. It's a multidisciplinary, and we can apply computer science knowledge in any domain. So engineering is not at all computer science only. Fine. So now we'll proceed with that, and I'll give you some examples. So there are chips like Intel, or you can say Lohi. So this is a Lohi chip, which is from Intel company. So these are mostly computing chips. Are many countries they are trying to invest, right? And they are trying to develop some kind of chip which is efficiently mimicking our brain. Okay, so it is efficiently mimicking our brain, so that it can parallel process the data as well as memorize the thing, instead of the von Neumann architecture. You might have heard about von Neumann architecture, right? So von Neumann architecture is a simple, there is a separate CPU, there is a separate memory. So always there is a back and forth of data transmission between CPU to memory. And if there is always a data transmission from CPU to memory, so it will consume lot of energy and lot of power. So to avoid that energy and power, we can go to neuromorphic computing or also in-memory computing. So in-memory means in memory itself you can do computing. So that is what is computing, right? So these are some of the examples how people have invested, or how the foundries have started investing on in-memory computing or neuromorphic computing. I have to from Purdue University also. So there is a center called BRIC. So what does it mean? So BRIC means it is a brain inspired computing kind of. So, and this center is open at 20, but it is accessible to all other universities. So, any company or industry or university, they can join together and they can do research on brain. So, how efficiently we can mimic the brain or how efficiently we can copy replace the brain. Right? So, these are a lot of examples I can give you. And again, like I told, these buzzwords. So, this is also one kind of buzzword, and it is going on for past 2 years or 3 years. So I can say it is just beginning, right? Because it will take longer time because you see the average time is taking 10 to 11 years coming to the market, right? So this is the best time to do some kind of contributions or some kind of research in this area. Going to like how to mimic. So I must say, what is the need, right? So what is the need means here if you see one typical picture, right? So a typical picture says me this axis is accuracy. Okay, so y-axis is accuracy and this axis is how many operations we are doing. So day by day, if you see your mobile phone also, there are a lot of features are coming, right? Lot of features are coming, and again, see the giga operations how they are increasing year by year. Okay? And you need memory also, extensive memory. So this is you can say small circles and how big it is happening, right? So these big circles are memory, and these are operations. So this is accuracy. To get a good accuracy, definitely you need large number of computations and you need extensive memory. So that is the main objective why people are going for in memory computing or neural instead of non-linear architecture. So whatever non-linear architecture is. Right? See, this is a typical picture. You can say one part is memory, another part is processor, and there is a bus connected between memory and processor. It uses a lot of energy and lot of power because you need always this communication between memory and processor. Right? So how to avoid that? Again, there may be some customization. And what is the customization? So people thought, okay, why can't we bring them together or closer, or together? How close we can make, right? Like you guys are sitting. So they started customizing it by bringing the memory and processor, bringing very close, some kind of customization, and with that they can able to do 8.1 tera mag. And what does it? So multiplication and accumulation, right? So definitely we need multiplication, right? So per second they can do 8.1 tera multiplication and accumulation per second with an investment of 36 watts, right? So this is from NVIDIA, and similarly you can see from Google GPU. So Google GPU also taking a customization of architecture and they are bringing a processor which can able to do 92 T max, 92 tera, or you can say multiplication and accumulation per second with an investment of 40 watt. So these are some of the examples from Foundry, right? Now if you compare with our brain or human brain, see human brain how much complex it is because there are a lot of, see there are a lot of thought processes, it is a lot of spiritual activity how to control our brain, right? So I can say it's very complex and it can do lot of extensive computations and memorization also, right? Which is not possible for any artificial system or HPC or any kind of supercomputer, right? Now, if you compare, we have a lot of neurons and synapses. You might be knowing about biological neuron and it is connected to some synapse, right? Like it's a data transfer. So we have three neurons, we have a post neuron, and there is a communication between three to post. Suppose some mosquito is sitting here, right? And till the stimulus is that high, I may not react. I'm sitting, I don't know it is taking my blood, right? And when the stimulus reaches the threshold, maybe the other hand will automatically go and hit, right? Trying to invest. Synapse connecting between three to post, and the synapse is taking care of the data transmission. When it reaches the threshold, it can make a connection between three to post. That's all, right? So we need neurons, we need synapses so that it can connect to a lot of neurons, lot of synapses, and the data can easily transfer from pre to post once the stimulus reaches the threshold, right? So please keep in mind, once the threshold or you can say stimulus reaches the threshold, then only there is a signal transmission between pre to post or there is a connection between pre to post. Fine. So now if you compare, we have 100 billion of neurons, we have lot of synapses also, and it can able to memorize many things, it can compute lot of things, right? But we can only consume power of 20 watt. So this is the beauty of human brain. It can do lot of complex computations, it can memory many things, but with an investment of only 20 watt of power as compared to the other you have seen, right? Google TPU, you have seen HP, here. So all this, whatever neurographic computing chips, all you can say the supercomputers and so on. So now compare these two. See, these two is one is volume architecture. I already explained. So this is CPU separate unit. This is a memory separate unit, right? So there is a communication between always CPU processor to memory. And this is one kind of neuromorphic when it's having only like brain architecture. And we can store, we can compute inside the same brain. We don't need a separate CPU or separate brain, right? But the only thing is, again, one more thing. Here, if you see our small computer, it takes binary data, but whatever we are speaking, it is like analog, right? So whatever we are seeing the signals, these all are analog signals, and they must be converted into binary, and again they must be fed to the computer, right? But now if you see the spiking neural network, they takes real-time signal. They don't need any analog or sorry, they don't need any digital data, 0 or 1. They need real-time signal, right? And it can take a spikes as input and it can give you output as spikes also. So this is only thing spiking neural network. Now moving forward, I can show you how a biological neuron looks like. You have a pre-neuron, you have a lot of post-neurons, and there are connections between pre to post. Fine. And we have dendrites, like synapses. So this synapse once, you can say the stimulus reaches the threshold, then there may be a fire. Okay, fine. So this is what it will happen, and the signal transmit happens between pre to post. Yeah, again you can compare with some other computers or it is like a Lincoln's a supercomputer. See, this is also a complex supercomputer. It takes large space and it takes 40 minutes to simulate 1 second of brain activity. Okay, so it takes longer time, and if you want to mimic the complete brain, it may take 6.5 years. Right? And similarly, you have some computers, supercomputers from Fujitsu, from other company, and they take 28 megawatt. So it's compared to brain, how much power it takes the brain. We don't take 21. So it's compared to 20 watts, see the power connectivity. Okay, and there are some examples. Again, we have nowadays you are using right a lot of AI, lot of AIs you are calling. Okay, open this play some music or this number, lot of things right in your mobile. So same way, we have some kind of vision because our brain has lot of sensors, right? And lot of sensors means we can see, we can visualize, we can smell, we can taste, we can tactile. So tactile sensors means we can touch and tell also whether it's a human being or whether it's a chair or something like. So this article says me, so we have a vision and we have a hearing also. So with that sensors, we can build a neural network and we can process some data and we can do some kind of recognition or classification. Whether it is or image classification that can be done or vision sensors or hearing, right? So this is what I was talking. So research is completely interdisciplinary. Now I can show you some movie. So if you see this is not a play. This to play. There is a video. So there is a video. I don't know why it's not playing. Okay. So this video says me. Okay. This video is from Peking University. And what is why you are laughing? Yes. Why so? You are yes. Why so? Not you. That's it. Yes. Okay. So now I will ask you any question. That's fine. I'll start you here and I'll ask questions from all your subjects whatever you studied. Okay. So now this video is not playing. And video of somebody, one guy is there and who is guiding the cycle. Okay, one automatic cycle is running here, and one guy who is giving instructions: go slow, go fast, and there is a bump. So slow down, take a direction of left, take a direction of right, and then move forward, rotate. So you turn. All these instructions are there, which was developed by Training University. How automatic driving, whatever you are doing, right? So how automatic driving can happen with cycle and through instructions, right? But I don't know, this video is not going, maybe it's not supported by Microsoft. So with that basic background, so I have some kind of neuron, okay? And these, and basically two items are there. One is neuron or synapses, right? So we have many number of neurons and similarly many number of synapses. They are interconnected and you can create a network for certain application. Now, how to mimic this neuron or how to mimic this synapse? So we have lot of people. So maybe you are having VLSI, right? CMOS or VLSI circuit. So through that NMOS and PMOS, again people can mimic the neuron, okay, or synapses. So, but the thing is here, if you see, there are huge number of transistors. How many transistors here? Anybody can count it here?